Alright, so in this video we're going to focus on elastic collision. So the definition of an elastic collision is one in which mechanical energy is conserved. Okay. In the previous video we talked about inelastic collisions, and we said that energy was not conserved. And so here that's really the difference between the two types of collisions I mentioned in the other video, is that momentum, regardless of the collision, will be conserved. Okay, and again, that's as long as the system is isolated. But in physics, we always assume isolated systems. But what happens is we go focus look at and we look at the really what amounts to the kinetic energy. And if the kinetic energy is conserved, it is elastic. If it is not conserved, it is inelastic. Okay, so and you can see here it says a perfectly elastic collision is an idealization, but collisions between two very hard objects, such as two billiard balls or two steel balls, come close to perfectly elastic. The collisions are going to have to obey two conservation laws. And what are they? Conservation of momentum and really conservation of mechanical energy, but really the conservation of kinetic energy, right? Because as long as it's done on the same level, right, we don't have to worry about potential energy, right? Because the potential energy, there is no height difference. And so for some of the problems, just analyzing the momentum is not enough to solve the problem, because you may have to determine the two final velocities after the collision. So this means that you do have to bring in that total kinetic energy, right? So sometimes it's just not enough to do momentum. And so just real quick, I'm going to give you two equations. Okay, these are equations that are not given by AP, but if you can memorize these will help you when doing questions that have to do with multiple. If you have to find, excuse me, this is V initial, V1 initial. If you have to find both velocities after the collision, and so the final velocity of the first object will be simply it's the difference of mass over the total mass times the initial velocity. Okay, and then again, I'm not going to show you the algebra how this, because it's like very tedious. 2 times mass 1. I don't know what to put a mass I. That should be a 1, right? Divided by the total mass, so m1 plus m2 times v1 final. Again, so we take all these equations, we mix them up into like a big batter, and so this is also assuming that v2 initial is 0. So to use these equations, if it's not 0, it just becomes like this long drawn out equation. But again, so some general rules about the mass velocity relationship. Again, assuming v2 initial is 0. If the masses are equal, what really happens is that v1 final is 0, and then v2 final becomes v1 initial. Okay, so if you think about billiard balls, it hits and it'll stop and keep going. Okay. Now, if m1 is much more, and that's what that double inequality symbol means, if it's much more massive, right, the first mass will barely slow down, and m2 will increase tremendously to the rate of v2 final would be 2 times v1 initial. Okay, and so that v1 final is going to be approximately, And so your V1 final will be approximately your V1 initial, right? They're not going to be exactly equal, but they're going to be about the same because it's going to barely slow down. Um, and then if it's the other way, it's kind of the reverse, right? So V final 1 will be approximately negative V initial 1. So it's like it would bounce off, right? And then VF2, right, would be 0, right? Because again, it's going to assume that it's at rest. So what really happens is, again, the opposite, like V2 barely begins to move, but V1 or mass 1 bounces off, okay? So here's a quick example. We will apply these equations to kind of just do this problem quickly. Again, this will be an equation you need to memorize, okay? So you have a 50-gram marble moving at 2 meters per second, striking a 20-gram marble at rest. What is the speed of each marble immediately after the collision? So to find V1 final, I'm going to use my M1 minus M2 over M1 plus M2 times V1 initial. And so I'm going to do 50. Again, I can keep it all in grams because everything is given to me in grams. And so I can just say 50 minus 20 over 50 plus 20 times 2. Okay? And so that's going to be 30 over 70 times 2. And so that's going to be 0.857 meters per second. Okay, and then our V2 final, we're going to use the other equation there, 2m1 over m1 plus m2 times V1 final. And so it's going to be 2 times 50 over 50 plus 20 times 0.857. And we can kind of predict, so m1 is larger than m2. So you can see that it does slow down considerably. It goes from 2 to 0.857, which means the velocity has to be transferred to the second one. So it's going to be 100 divided by 70 times 0.857, right? And so that's going to be equal to 1.22 meters per second. Okay. I do want to show you this kind of like, not like cool trick, but there is a kind of a relationship between the velocities, if you want to say. And so I apologize. I'm not gonna. I'll do a video on that later. Okay. And so this is, again, we're using these shortcuts to do this calculation, right? This becomes very long if you kind of want to do this as a doing momentum, conservation energy, and so forth. So if you can memorize these two equations, that would be very helpful, beneficial to you. I could do I probably will do a video to show where these two equations come from, especially with if so these equations assume that the second object is not moving initially. So what I can do is show you what happens if we don't make that assumption. Okay. So in the next video we're going to look at explosions, and we'll look at two-dimensional collisions, and then we'll also look at ballistic pendulums.